say I take two scalar fields, phi1 at point x1 and phi2 at point x2. Okay, this is an embedding space. Okay, in principle, two different scalar fields at two different points. Okay, and I want to get.
Existe capital claro, né? Capital
Yeah,
claro. Okay.
Okay. This we know this has Lorentz invariance. Okay, rotational invariance. So the most general form this guy can have is say constant here. Shall call xc12, 12 for the two fields, and I'll comment something more about this. Okay, that's scalar product between the 2 points that are okay. First thing, we only have Lorentz invariance in the embedded space. You do not have Poincaré invariance in the embedded space. That's why I'm not using anything like this. Okay, in the embedded space, I'm only using dot products. Okay, because dot products are represented by Lorentz transformations. Second thing, okay, you might wanna. You could do this dot product here somewhere too. Sorry, this one. But this one on the line one it vanishes. Okay, so I'm not considering this. Okay, P0, same thing for S2, S2. Okay, say this. Taking the Poincaré section already. Okay, and then this factor here, the reason I just put power law here in terms of this dot product is because of this homogeneity condition here. Okay, if I do a Lorentz transformation, we'll get out of the physical space section and I just have to scale back, and the supposition is that the fields just rescale. Okay, this is the only form that is consistent with this rescaling. Okay, and this is the reason I just call this minus delta here is just because physically you expect correlation functions to decrease with distance, right? If you have correlations running with distance, then your theory typically has some kind of units. Okay, probably renormalizability, unitarity, and so on. Okay. Any questions? No? Okay, so this is the most general Lorentz invariant 2-point functions of two different scalar fields at two different points in the Poincaré section. So let's now actually use this result here. Okay? The dot product just becomes I'm going to get 2 delta here because I have that square there. Okay? And the minus 1/2 I just, if you want, really will absorb here in the constant. Okay? I used we had this scalar product on the embedded space. Right? But we just discussed that the scalar product in the embedded space, when restricted to the Poincaré section, just becomes this. And the minus half factor, I just used to redefine the constant. Okay? And this was what you would call alright? This is in physical space. Okay? So that's it. That is the most general 2-point functions in a conformal for scalars in a conformal theory. And, it seems like an overkill. I have to talk all about that, like formalism, but one entire class just to get that. And the point is, there are many ways to get n-point functions, 2-point, 3-point, and 4-point functions in conformal theory. And for scalar point functions, the embedding formats might be kind of say overkill if you want. but it really starts to shine when you start considering the correlation functions for a different scheme. Okay, that's the whole point of this paper and introduced. Because people knew how to deal pretty well with scalar field theories and conformal scalar conformal field theories, but say spinning conformal field theories are a bit more cumbersome to derive the constraints and correlation functions. So, and the point is that they stay relatively simple if you try to find the correlation functions using the Rychkov formalism when you consider spin. There are additional, you have to talk about more suppositions here to what happens to your field when you restrict to the Poincare section. You have some transversality conditions and so on that again don't have time to discuss here in this section and this lecture. But just was so simple, right? And the deconstruction guarantees that this is conformal invariant. Okay? The usual way that you find on books to derive this is just to say, okay, scalar field, 2-point functions, right? For a scalar field, by Poincare invariance, this must be some function of the distance only. Okay, by Poincare invariance. Then you say, okay, if I do rescalings, then I just have that kind of condition. Have something like this. And then just reduce two functions, and then you solve this, and what you obtain is this form. What you actually obtain is would be something with, say, delta plus 1, delta plus 2 here. You could have, in principle, have two different scaling dimensions for this two scalar fields. And then what you do, you impose the special conformal transformation, and then that's where it starts to get messy, because again, the special conformal transformation is a non-linear transformation. But for 2-point functions of scalars, and you can just solve it quickly, like in 5 minutes. And what you obtain, the SCT constraint actually tells you that delta 1 has to be equal to delta 2. So we call this the delta, and that's why we obtain 2 delta here. Okay, so using the Rychkov formalism, it can become a bit more. You can lose sight of what each of the conformal transformations do, but Poincare invariance is just correlation invariance tells you that the correlation function must be a function only of differences of space-time points. Rotation invariance then further restricts this and say that it can depend only on the length of separation of this space-time points. It can depend only on the distance. Then scaling tells you that we get this scaling factor in front. And if you try to consider different fields, then you could have different scaling dimensions. And then if you impose the special conformal transformation, what it does, it actually constrains the scaling dimensions. Okay? For 2-point functions, you say that they must be equal. Otherwise, the correlation function must vanish. Okay? And this can go undisturbed in the Rychkov formalism, because the formula is just so powerful that we don't have to worry about these things. Say, if I wanted to, I cannot introduce here, I'm taking 2 different fields, 2 different scalar fields. But if I try to do this, okay, say if the first field has scaling dimension delta 1, I should have a delta 1 here, okay? And then the second scalar field has a scaling dimension delta 2, I have a delta 2 here. But I must form a Lorentz invariant with these guys. And the only way to do this is a scalar product, but I can only do this. These guys are equal. I don't have any other ways to do this. Okay? So in the embedded formulas, this is just that these guys have to have the same scaling dimension. It's just like automatic. You don't need to think about it. Okay? While in the most pedestrian way, you have to impose and have to take the conformal generator, apply the correlation function, then obtain something here and solve for it. Okay? So when you start considering spinning particles, spinning fields, then it just starts to become too cumbersome. Okay, things quickly get out of hand. When this form is in a bit more constraints, you can just take spinning coordinates much more easily. Okay. That is it. There are any questions about the 2-point function? No? Okay. So let me just write this here for completeness. This is the only advantage of doing the pedestrian way, because it becomes more clear what each transformation is doing. And usually, we can normalize this any way we want, and then the usual choice is just to take this constant P1. Okay? But in doing so, the higher point, the 3-point, 4-point correlation functions won't have this freedom anymore. Okay? And the reason why we'll come to maybe 2 or 3 lectures. The 3-point function is still really, you just repeat this this idea. You have to, you start from already thinking about the Poincaré section. What do you should have like calculus bits x1 dot x2 with some exponent here of alpha 1, 2, 3. Should be something like this, okay? By the same line of thought. And then actually implementing this Poincaré section, we'll obtain here in the denominator. We'll obtain x1 minus x2. This guy here, then you have some linear system here, because we have now 2 factors of x1. Okay, so alpha 1, 2, 3 here plus alpha 3, 2, 1, 3, 1, 2 should be equal to the scaling dimension of the first field. Okay, and then similar for the other one. Okay, you take alpha 1, 2, 3 plus alpha 2, 3, 1 has to equal delta 2 and so on. And it is there are 3 variables, 3 equations that can solve this explicitly. And the results just that actually not this no the scalar products become these differences. Any minus side factors are absorbed into the constant, doesn't matter. And here we have where the delta with no so index is just delta 1 delta 2 plus delta 3. Okay? Just this comes from solving this system. Alright? Any questions? So what conformal symmetry does, it completely fixes, it completely fixes the formula of 2-point functions and it fixes the form of 3-point functions, except for this constant here. Okay? If we rescale the T12 constant and 2-point function to 1, which we usually do, then we cannot fix this constant. Okay? This constant will only be fixed with dynamical consideration. Okay? It will depend on the theory, on the CFT you're talking about. Okay? This is the subject of the operator product expansion that we come to in 2 or 3 lectures, I don't know. Okay? But kinematics fixes the functional form of the second of the 2-point function. It fixes the functional form of the 3-point function, except for the constant that is fixed by dynamical considerations. And I won't do it here because it takes too long, but you can already suspect that the 4-point function won't be constrained as much as this, because we'll have 6 factors here, right? We'll have 4 points, x1, x2, x3, x4. So you could write 6 Lorentz scalar products here. Okay? But you only have 4 points. So we have 6 variables for 4 equations. Okay, so what this implies, as we will discuss in the beginning of the next lecture, is that the 4-point function is constrained. We will have some factor like this in front, times a function of some variables, and this function can be arbitrary. Okay, so you can just think like this constant is replaced by a function, a whole function of 2 variables. But we'll understand this in the beginning of the next lecture. And the reason is that because we have 6 variables, 4 equations, we have 2 more degrees of freedom. Okay, here we cannot fix using only this kinematical consideration, okay, conformal symmetry. But looking ahead, the operator product expansion, which will be basically the main result of these lectures, is what allows us to fix that constant on the 3-point function and compute these 4-point function and 5-point function, whatever point functions you want in terms of the 2 and 3-point functions. Okay, there will be some kind of recursion relation. Okay, but these take into account dynamical considerations, so it depends on the CFT you're talking about. Okay, these are only kinematical constraints from conformal symmetry. Okay, so I went here. Unless there are questions.
Is there some factor 1/2 missing or something?
I just absorbed in the constants.
No, I mean in the deltas. Because if I take
On the
alpha 1 to
deltas,
3
there
plus,
might be.
should be divided by 2.
Probably. Because on my notes I stopped it for some reason. But there might be.
Just delta 1 plus delta 2 plus delta 3 over 2, something like that.
We can solve this.
Yeah, okay. But I just want to make sure. But it's,
There might be. Okay, I'll come to that. There'll be an errata in the beginning of the next lecture. Okay, but yeah. Right. That could be eventually or something like that. Okay. So you can just solve this. Any more questions?